So here we are on the course web page, which I'm sure you know how to get to. In particular, it's linked to from my homepage. And today we will be using this set of slides on the economic mechanisms in ATM. And then after the class, I will put the link to the recording right below the slides, as was the case with all the other slides and the lectures. And this class is based on a paper that Tobias and I wrote some time ago. It is about resource allocation in air traffic management. But the things we will be talking about today are really very general market mechanisms which work in lots and lots of other places, not only in air traffic management. And we will be looking at some very general questions, in particular understanding why money is needed. So the generic question that we want to look at is we want to look at the market. So there are certain users that enter the market, and users have money. And there are also certain resources that the users are interested in. And today we will assume that there is a single owner who owns all the resources. There may be also other models, but this model is interesting and general enough. And so the users express their interest towards resources by placing bids. So basically bids represent some kind of information that the users have how much they like different resource allocations, how much they like different resources, so sets of resources, so whatever. We will get to some concrete examples, but in the general setting, the users just place some bids for the resources. So think about the auctions, you know, like an item is being sold and the users tell the owner how much they like one item. So what happens next is that the resources get distributed to the users in one or another way. So some resource allocation goes on, and then the users pay to the owner, and the market clears. The resources are sold to the users, the owner gets some money, done. Very, very generic scheme. And the question that we will be looking at is, what are the rules that govern such markets or markets in general? Immediately an example very much related to air traffic management, slot allocation. So you have certain slots at the airport. So over here you may see, well, the slots are numbered. Sorry. Yeah, I mean, slots have numbers, and then there are different flights that come in and get allocated different slots. This is a very standard procedure in air traffic management. Slots distributed to flights. Other examples, again, speaking of time slots, conference programs, there are different talks in a conference, and the question is which talk goes when. Or you may think of a class schedule, which classes are being given at which times, if we think about classes as resources in any way. Another example, well, it's also related to air traffic, well, to air traffic, because I took an example of an airport, but it doesn't have to be an airport. In general, in a shopping mall, allocation of different kinds of shops. Where do you put different shops? People may have different preferences, businesses may have different preferences with respect to where their shops are located. And yeah, so some of the questions that we may ask ourselves in these kind of bid, allocate, pay mechanisms, when the users express their bids, the resources are allocated and payment is solicited from the users, is yes, what info do we ask the users to produce? Of course, we want the users to produce true information, the true bids. The next important question is, how do we allocate the resources? Whom do we give what? Who gets which place? And last but not least, how much the users should pay? What is the price for the resources? And well, and another question which I also have separately here, what is the computational complexity? How do we compute the allocation of resources and the prices? We will be not touching too much on that, but that question is still with us. Maybe it's a hard optimization problem to compute the optimal allocation of resources. And well, come to think of it, we could have had some kind of a session if we were really in an economics class, or we could have looked at the history of economics. People have asked these questions for at least about 50 years. And they were thinking of desirable properties of market mechanisms. And some of the properties that people came up with are as follows. So there is the social optimality. So the resource allocation should be good to the society, right? We shouldn't give all the resources to a single user or allocate the resources in any other unfair way, whatever unfair means. So the society should be happy with the allocation of the resources. Incentive compatibility, well, basically that users do not lie, that they submit their true preferences, that they place true bids. Would be nice. Individual rationality, we'll have more details on that, but basically the idea is that the users shouldn't be extorted of money or utility. We shouldn't go around and say, well, we have allocated, one pencil to you, and now you owe $1,000. So users should be happy when they enter the market. They should have non-negative utility. We will define the utility in a very precise way soon, but in general, the markets should be such that the users are willing to enter the market. And the last one is budget balance. You don't always have to have that. Sometimes the owner may make money or may subsidize the trade, but sometimes it also makes sense that the resource owner doesn't earn money or doesn't lose money. So it just redistributes the resources. And that's called the budget balance. So as usual, there is, of course, lots and lots of terminology. So this social optimality is often called social welfare maximization. So we want the mechanisms or markets to be socially optimal, meaning that they should maximize social welfare. Again, we'll define it in a precise way soon. Sometimes the social optimal mechanisms are also called efficient, but we will not be using this because efficient often refers to computational efficiency. This incentive compatibility of mechanisms, they meaning that that the users do not lie. Incentive compatibility is often called truthfulness, and I like this truthfulness because that's something that at least speaks to you what the mechanism is about or what this property is about. So truthfulness means that the users submit true info or at least do not benefit from lying. And the reason why it's called incentive compatibility, well, it means that, well, the users have certain incentives, true incentives, and the mechanism should be compatible with those incentives, should not incentivize the users to lie. But I think truthfulness is a better notion. Sometimes these truthful mechanisms are also called strategy proof. And we will not be using this, but the reason behind this name is that the users shouldn't be able to strategically manipulate the mechanism. So there should be no strategy for the users like, okay, I will not submit my true info, but instead I will strategically submit some other information and gain something. And the mechanism should be strategy proof. So that's why incentive compatibility is sometimes called strategy proofness. And this individual rationality, the idea that the user should be happy from entering the market or gain non-negative utility is sometimes called the participation constraint, meaning that the users, well, want to participate in the market, or at least do not want to not participate. So the utility should be non-negative. Anyway, they should be happy or shouldn't be unhappy. And if we look at these properties, they're not completely independent. One of the things is that if you want a socially optimal mechanism, then the mechanism should better be incentive compatible. Because if the users do not submit their true information about how much they like the different resources, how are you going to know what is socially optimal and what's not? If people don't tell you what they like, it's pretty hard to make them happy, right? If you know if you truly know, if the people tell you the truth, how much they like different things, well, then you have at least some chance to make them happy. Of course, there are all these issues with the privacy and so on. People are not willing to tell you their preferences, what they're happy about. So there is an interplay, how to make the mechanism truthful so that later you can possibly make it socially optimal. There is more, so we will speak more about these connections between the different desirable properties, but at least there is one which I mentioned right now. If you want a socially optimal mechanism, well, you should know what the society wants. You should know what the users want, what their preferences are. But going a bit further, there are some classical results in economic theory which say that no mechanism can have all these four wonderful properties at the same time. It's a bit unfortunate, but not entirely unexpected. In economics, and in particular, well, I don't know if social choice is really part of economics, but anyway, in this kind of sciences, in social sciences and economics, there are quite a few impossibility results. One of the results that you may know is about the voting schemes, that it's practically, well, not practically impossible, theoretically impossible. There is a result which says that you cannot design a voting scheme which would simultaneously satisfy certain desirable properties. That the only voting scheme which satisfies those properties is actually a dictatorship. So there are quite a few impossibility results. The one that we are particularly concerned with right now is that when it comes to the market mechanisms, you cannot satisfy all these four properties. There exists no mechanism like that. Okay, so there is no silver bullet, but you nevertheless may try to design different kinds of mechanisms. And the work on mechanisms is huge. In particular, there is a large body of work on market mechanisms in air traffic management. One of the earliest works on auctions was actually on slots auctions in air traffic management, dating back to the 80s. More recently, again, the slot exchanges were considered in some work. The auctions in general, the generals were also considered. There were also some recent paper by our Italian colleagues, and in those papers that were appearing about 10 years ago, they were designing mechanisms that were individually rational and were budget balanced. They could have been made socially optimal, but of course, since you couldn't have all four properties, their mechanisms were not incentive compatible, not truthful. So they designed mechanisms with three properties, but not with all four, unsurprisingly. And something that we looked at with Tobias is then what I will be talking about today is mechanisms which are socially optimal, truthful, incentive compatibles. They are possible to make individually rational, and I'll show you how to do that. But, well, unsurprisingly, they are not budget balanced. Okay, so that's more or less setting the scene. Maybe I should ask if there are any questions before I'm going into the formalities. Recording. So formal definitions, quite a lot of mathematical notation ahead, but at some point things will hopefully be more clear with the notation than otherwise. So the simple notation is for the users. So the users or the agents or whatever you want to call them will be just denoted by numbers 1 through n. So there are n users. Then we will have this notation, capital A, the set of all possible allocations of resources. So all possible ways in which you can think how to allocate the resources to the end users, that's the set A. And in the example of the slot allocation, so let's say we have 3 users and we have 3 slots, slot 1, slot 2, slot 3. Well, you can allocate the slots like this. the first slot to user 1, the second to user 2, the third to user 3, or you can allocate the slots like this, or like this, or like this, and so on. So you can actually, in this simple example, you can enumerate all possible ways of allocating the slots to the users, so you can explicitly enumerate this set, capital A.
Can I ask something?
Absolutely.
Why is there in the fourth column there are 2 users?
My bad. I'm sorry. That's a typo. Thank you.
So it's the same as in the last column.
It shouldn't be the same. It should be different because there should be 6 different. Let's see which of them should be user 3. Well, probably this one.
Okay.
The one in the middle. Thank you for mentioning it. Oh, wow. I've been teaching this for 7 years? That's first time. Right. So this should be user 3, and then it will be hopefully different from all the others. 6 ways to permute or allocate 3 slots between 3 users. Thank you. I'll try to remember to change that. Or maybe I'll keep it for others to spot. Right. So here we have this set A listed explicitly. There could be other ways to list the possible allocations. Okay, the next thing, very important thing, the valuation. So what is the valuation? Well, it's really a function. It's indexed by the user, and it's the function of an allocation. So given a certain allocation A from the set of all possible allocations, you can assign certain number to it for user I. It can be some, well, monetary value, some way to measure how happy the user is about this allocation. So it's really a numbers and a number. And here I'm saying that this valuation is a function from the set of all outcomes into the set of real numbers. The valuation can be negative. So the user may be unhappy about an allocation. Maybe the user gets an unfavorable resource, or maybe is asked to pay too much for the resource. But anyway, the valuation is a function which shows how much the user I likes an allocation A. So we can say that the user I has valuation for each outcome. We can also say that the user is this valuation function, has this valuation function, but we can also say that the user is this function. Why? Because this function is the one and only thing that we care about. So we don't care what is the user's name. I don't know if it's we're talking about air traffic management. It doesn't matter what airline it is, what airplane it is, how many people on board, whatever. All we care about is how much a particular flight likes a particular slot. Wherever it comes from, whatever the origin, the ownership, and anything else, all that doesn't matter. One and only thing that we care about is how much the user likes a certain outcome, certain allocation of resources. Okay, so that's the valuation. Now, how the valuation is specified? Well, as any function, it can be specified as a table. So here we have different outcomes, different allocations of the resources, and for user I, here we say how much the user I likes every allocation. It could be a table. Or a function may also be specified with formulas. So for instance, we can have a valuation like this. So user I is less and less happy the later slot the user gets. So this is a linear function. This is some constant. And this is some weighting factor. And yes, so it's, of course, it's weighting in the sense that it's a weight, but it can also be called weighting factor, that if the user has to wait for one slot, then the user loses WI in his or her valuation. So for the first slot, the user is getting CI minus WI. If the user gets second slot, the valuation of the happiness of the user is CI minus 2 times WI, and so on. So the later slot the user gets, the less happy the user is, and the user's valuation, the user's happiness goes down linearly with the slot number that the user gets. It makes sense as a valuation function. Now, we will consider something that may be called selfish, rational, envy-free user, and will not go into all the details of what each of these things means. But in general, most often the users don't look at what the other users get. They look at what they get, right? So an allocation, remember, an allocation of resources is not only what you get, but also what all the others get. And if you are selfish, rational, and envy-free, then you don't care what the others get. You only care about your own resource. But sometimes it may make sense that your valuation may depend on what others got, even if you are selfish, rational, and envy-free. So here are some examples. I mean, these are the stores in an airport, and I don't know, maybe if you owe the store for Omega, you do care where you are located. I mean, depending on where the entrance is or whatever. But at the same time, you may care about where other, like your competitors, are located. I don't know whether you want to be next to them or far from them. I'm not an expert in high-end watches, but anyway, sometimes you not only look at your own resource, but also the resource of others in order to evaluate how much you like certain resource allocation. Again, another example, conference programs. Of course, mostly you care about when your own talk is scheduled. You don't want to be the last talk in the conference or whatever early in the morning. But sometimes you also care about talks, scheduled in a parallel track. So maybe you have to speak here, but there is super interesting talk here. So then you not only care about your own resource, but also about resources of others. And coming back to our running example, to the slot allocation, in principle, you only care about which slot you get. But what happens is that you may have an outbound flight. So maybe you're arriving, I don't know, here at some point of time, and maybe there is some slot that you will get among these. And well, you may want to get the earliest slot, but maybe there are also other inbound flights. And before you depart, all of these have to land because maybe you have connecting passengers from those ones to your aircraft. Remember the TNFL 07. And so then you not only care about your own slot, but you also care about arrival of one of these flights from which you have the connecting passengers. Again, that's just an example when your valuation may depend not only on your own resource, but also on what others got. Just examples. Let's continue with the definitions. So the allocations, some allocations are good, some allocations are not so good, we know. And one quite natural way to measure how good an allocation is to look at the total valuation of all the users. So you have a certain allocation of resources, A, this is how the resources are distributed, and user I has this valuation for the distribution, for the allocation, and this is just the total happiness of the whole society. It makes sense. That's called social welfare. And again, a natural definition, a socially optimal allocation is the one that maximizes the social welfare. Quite natural. What else could it be? Again, in the now running example, the slot allocation. So we have n users on one side, and we have slots on the other side. And what is an allocation here? What are we looking for? Well, we're looking for a matching. So every user has a valuation for a certain slot, and we want to match the users to the slot, one-to-one matching. For instance, something like this. And the socially optimal allocation is the one that maximizes the weight of this matching. Okay, so we are matching users to slots in some way. And every user has certain happiness, certain valuation over the slot that the user gets. So every matching or every allocation has certain valuation for every user. And if you sum up those valuations, you'll get the social welfare of the allocation, the social welfare of the matching. And the socially optimal allocation is just the allocation that maximizes the total user's happiness. So let's look at this very specific example of valuations, these linear valuations. So for every user, while we have some happiness, while the user is happy that if they land at the airport altogether, so consider these are like airport slots and the users are the flights. And of course, everybody is happy about being landed at all. But then the later you are landing, the larger the S is, the later the slot that you get, the less happy you are. And the rate at which your happiness goes down is WI. If you are user I, then every slot that you have to pass, your happiness decreases by WI. Again, it can be measured in purely quantitative terms like the fuel or passenger unhappiness. There is also this value of time for the passengers, for the airlines, and in general, this something, I guess Yolanda mentioned at least this cost index, which trades time for the fuel when you were talking about the trajectory optimization. So anyway, time is money, we know that. And the later you land, the worse it is for you. How bad it is determined by this coefficient. This coefficient may be different for different users. So some of the users may be very impatient. And in fact, we will assume that the users are ordered by their impatience or by their weights. So the user 1 is the most impatient. You know, if the user 1 is delayed by a single slot, maybe he loses 10,000 euros. User 2 is less impatient. You can delay him by 1 slot, and he uses 5,000 euros. User N, well, doesn't care too much. You delay by 1 slot, maybe he loses $1, maybe loses nothing. So we will assume that the users are ordered by their impatience. Okay. And if that's the case, then the question is, what would be the optimal allocation? What would be the socially optimal allocation? How would you assign slots to the users? So you know you have to match the slots to the users 1-to-1. Whom would you give the first slot? Maybe to the one who is most impatient, right? You don't really want to delay user 1 by a single slot, because if you put user 1 somewhere else, not in the first one, oh, the user loses like lots and lots of money. You don't want that. And user N, well, that's perfectly fine to delay him forever because, well, who cares? His waiting or impatience coefficient, so his weight is so low, maybe it's equal to 0. It doesn't matter when you land that user. So it makes sense that the socially optimal allocation puts users, assigns users to the slots in the order of users' impatience. Okay, hopefully that makes sense to you. And then let's think. If we ask the users to report their valuations, let's say to report their weights, how impatient they are, how much fuel or time or whatever they lose if they have to wait for 5 minutes for a single slot. Then, of course, every user would be willing to get the first slot. So every user would be willing to say, oh, I'm so impatient. It costs €1 million to delay me for 1 minute. So the users will be willing to misrepresent their evaluations, misrepresent their info. The mechanism will not be truthful. So if you do this wonderful socially optimal allocation, asking the users to report their evaluations, well, they can also report this, but that kind of doesn't matter. That's a constant, doesn't depend on the slot. So you would be asking the users to report their weight factor or impatience or whatever you want to call this, how much the users lose from being delayed, from being assigned to later slots. The users will have the incentive to lie. Whether they will lie or will not, that's a different question. That's ethics or whatever. It's not discussed here. They have the incentive, and that's market, so they will. So it's bad. So how can we make sure the users don't lie? Before we answer that question, let's again look at the things in a very formal way. So what do we really do as the resource owners? So we can say that we look at the world, and I put it in quotations because this is not a standard term. I'm just using this to denote a set of users. So we have a set of users, and as we discussed, every user for us is just the valuation function. So we have a set of valuation functions. We have a set of agents with certain preferences. And we can define the set of all possible worlds. All possible worlds, meaning that all possible vectors of valuations. And the particular world we are looking at is just some vector from this set. Okay, so and users with certain valuations. So as the resource owners, what do we really do formally? Well, we look at the state of the world. We see, okay, we have such and such users today. I don't know, certain airlines with certain valuations, certain flights. And having the users as today, we have to do the resource allocation or choose the resource allocation from the set of all possible resource allocations. So essentially, given the state of the world, given a set of users, we have to choose how to allocate the resources to them, right? I mean, I'm being formal, and maybe being formal takes away the clarity, but still, that's what we do. We have certain users, we have to allocate the resources to them. So in the very formal setting, we have the set of all possible worlds, all possible users. And what we really do is we execute the social choice. And it's a function from the set of all possible worlds to the set of all possible allocations. So essentially, given certain users, given certain world, we decide which allocation to give to the users today. Okay, it's just formalization of what we do as the owners. And our things like that we defined before, like for instance, the social optimality, it can be written like this. So the social choice function maximizes social welfare if it chooses the allocation that maximizes the total valuation, the total user's happiness. Okay, so that's a socially optimal social choice function. Okay, it maximizes the welfare, maximizes the total user's valuation. So again, coming back to our example of slot assignment with linear valuations, the socially optimal social choice function will allocate the slots in the order of decreasing impatience or decreasing weights. And again, as we already discussed, this is not truthful, not incentive compatible. Every user will want to be the user one to get slot number one, and will have the incentive to lie to the mechanism. And now, before giving you the answer how to avoid that, maybe you have some suggestions. How could we make sure that the users don't lie? Or what should we use for that?
We could maybe make them.
That's what we should do. This is why money is needed. The users have to pay for their allocations. It's not enough to just announce, you know, I like the first slot very much, and I like the first slot very, very much. And the more varies you say, the more impatient you are, the more chances you get to have the first slot. You will have to pay for the allocation. Then at least there is some hope of making users truthful. So here is our kind of, well, not the final, but maybe the biggest definition of today. And this is the time when maybe all this notation starts to pay back and make things, well, more clear than cumbersome. So this is mechanism with money. So F, as before, is a social choice function. It looks at the users and decides an allocation. So here are my users today. They have such and such valuations. Okay, this would be the allocation that I decide for them. But also we have another function called P for payments. Again, it looks at the users and decides for every user how much the user will have to pay. And this payment can be negative, meaning that maybe we will pay to a certain user. So the payments may go both ways. The users pay to the mechanism may also pay or compensate some of the users for unfavorable allocation. Okay, so not only that we allocate the resources, we also enforce payments from the users. And here is something that, well, I guess it has some fancy name like quasi-linear utilities, but whatever. The utility of every user is the valuation that the user has minus the payment. Okay, so I have certain happiness over an allocation. Oh, I'm so happy with the slot. I don't know, I'm 100 euros happy about this slot, but I have to pay 20 euros, so my utility is 80. Again, it makes sense. So the utility of the user, kind of the final happiness, is the happiness with the allocation minus the unhappiness with the money. Okay, so that's the formalization of the mechanism. Given the users, you choose the allocation, enforce payment, and the utility is this. So this is the same as on the previous slide, but just with the formulas. And now the formulas are shorter. I don't know if they are more clear, but that's what the formulas are for being shorter. Social optimality, as before, we want to maximize the social welfare. But now with all these things that we have defined, we can also formally define incentive compatibility, that no user has the incentive to lie to the mechanism. And this is a super heavy notation. You don't have to go through all of it, but essentially what it says is that we can consider two worlds, this V prime and V star. And in both worlds, all the users except for the user I are the same. So they have the same valuations. And for the user I, in V star, the user I submits his true preferences. So this is the true valuation. This is the true user. And in the world V prime, the user I lies and submits something else, V prime I. Okay, so this is wrong. Here the user lies, and here the user is truthful. And incentive compatibility of the mechanism in the formula, in the formal notation means this, that the utility that the user gets in this world, where the user submits his true preferences, is at least as large as the utility of the user in this other world where the user lied. Okay, so again, the formula is simple, and if you know all this notation, then it makes sense, but more or less it says there is no need to lie. If you don't lie, your happiness is at least as large as if you lie, no matter how you lie. So that's the incentive compatibility. Very strong condition. So no matter what the user says, if the user doesn't say the truth, then the utility goes down or stays the same. But you can never gain, you can never have the incentive to lie by misrepresenting your preferences. Okay, so that's the incentive compatibility. And again, for the slot assignment with linear valuations, we know the socially optimal allocation. Now the question is, how do we make sure that the users don't lie? Okay, we enforce payments. Yes, that was the right guess. But which payments to enforce? So how much should we charge the users so that they don't lie? I mean, we can do some random shots in the dark. I'm quite sure it's quite complicated to come up with the scheme which ensures that the users don't lie. And by default, it's not even clear that such a scheme exists. So you can say that, well, let's not charge anything from any of the users. Well, then we are back to mechanisms without money, and we know the users will have the incentive to lie, to misrepresent their utilities. Everybody will try to become the user number one. We may hedge against that and say, well, okay, the user number one will have to pay a lot, 1 million euros for the first slot. Well, okay, so now we solved one problem. Nobody wants to get the first slot because they will have to pay 1 million euros. But still, the users will be afraid of telling their true preferences, because if they do, somebody may turn to be the user one, the one with the highest impatience. Maybe it's, I don't know, largest airplane, or there is something very urgent that they really need to land in the first slot. But well, they would have to pay too much. So again, the users will be afraid of telling the truth. They will be afraid of giving their true preferences. The mechanism, this will not make the mechanism incentive compatible. We will just solve one problem, but open up some others. So what would be the right answer? How do we do the right charging scheme so that the users do not misrepresent their preferences? So I suggest we take a break here. I'll pause recording. So yes, we are still on this slide with the slot allocation example, linear evaluations, simple but natural. And the case when we know that the socially optimal allocation allocates the slots in the order of decreasing impatience. The most impatient user gets the first slot, which makes the user wanting to lie to the mechanism. And so that they don't do it, we think, oh, maybe we have the first user, or the users who gets the first slot pay 1 million euros. Well, that's not gonna solve the problem, because then the users will not be willing to become the user number one. So we'll continue. But yes, this slide has a $1 million note on it, and I will use it again. These are really $1 million questions. How do you make the markets truthful and social optimal, and so on? And it's amazing that actually the answer exists. When I was a student, we used to have a teacher who would say, I'm going to tell you a result today. Once you see it, you'll never forget it. And then we would continue joking, saying that the teacher next says, what was this result? What did I supposed to talk about? So maybe today I have this feeling that this really should be a result that once you see it, you never forget it. Why is it even possible to use money so efficiently that we get the market mechanisms which are socially optimal and incentive compatible? But again, before giving you the answer, of course, I could have given you the answer on the first slide. I'm still trying to kind of prepare the grounds for it. Before looking at social optimality and truthfulness, let's look at other properties of the mechanism. Just recall what they are. The individual rationality. We want the users to be happy with the markets. And with our notation, we can now give the exact formulation for it. We want to say that no matter what the users are, your social choice function and your payment function should be such that for every user what the user gets, the valuation, should be at least as large as the user payment. We shouldn't ask the users to pay more than what they get, or their total utility should be non-negative. So again, it's just an illustration of how the simple things stated in simple formulas, but of course all this notation takes some time and effort to appreciate and learn. We don't have to do it all the way, but just an example. Similarly with the budget balance, just to remind you, budget balance means that the mechanism is budget balanced if the resource owner doesn't earn anything and doesn't have to subsidize the market. And again, in our terms, it just means that no matter what users you have, the total payments that they make should be equal to 0. They shouldn't pay too much. They shouldn't get anything from the mechanism in total. But different users may pay something and get something from the mechanism. And again, just to show you the, well, not necessarily the power of the formulas, or maybe the power of the simple language, these 4 properties of the mechanism: social optimality, truthfulness, individual rationality, and budget balancedness, may be stated in these purely mathematical terms like this. So social optimality, you're maximizing the social welfare. Incentive compatibility, you have no incentive to lie, because if you misrepresent your preferences, you're getting less than from being truthful. Individual rationality, you're getting non-negative utility. And budget balance. And again, what's the main question is, how hard is it to design a mechanism? Well, let's see. Let's start from individual rationality. So we want to design a mechanism which is individually rational, or which makes the users happy with the mechanism. If you only want a mechanism which is individually rational, that is, you want to make every user happy, can you do that? Can you do just that? So forget about social optimality. You don't have to distribute the resources in any good way. The users may lie. What else? The mechanism shouldn't be budget balanced. Just you want to make the users happy. Can you do that?
It
Remember?
seems difficult to make all the users happy.
Well, that's true. But remember that when you are designing the mechanism, you're designing the social choice function, the allocations, and the payments. And you have the full freedom in how you allocate the resources and how you make the users pay, or how you pay to the users. You don't have to be budget balanced or anything. You just want the users to be happy. So these payments that they make or receive could be arbitrary. If you have all the money in the world, you in principle can make users happy, right? Make a mechanism which pays an infinite amount to something very large to every user. It's not realistic, but in theory, just making the mechanism individually rational, just making the users happy, well, it's possible. Just pay a lot. Budget balance. So you want that the resource owner doesn't gain anything, doesn't earn anything, but doesn't lose anything. Can you design a mechanism which is budget balanced? Again, forgetting about all the other properties. Doesn't have to be individually rational, truthful, socially optimal. Just make sure that the resource owner doesn't receive any payments, doesn't get any payments. Can you design a mechanism like that? Again, remember that you are designing both the social choice function, that is the resource allocation, and the payments. And if you're completely free with the payments, well, you can say that if there is any imbalance, then user 1 pays the imbalance, so user 2 pays the imbalance, or it's equally spread, or nobody pays anything. Let's get back to the mechanism without money. Nobody pays anything, nobody gets anything. So if all the PIs are equal to 0, well, the mechanism is budget balanced. So by itself, budget balanced is not too complicated. By itself, individual rationality is not too complicated. How about making the mechanism individually rational and budget balanced? So the users just redistribute the money between themselves, but they all have to be happy. So each user gets no negative utility, and the total amount of money is constant. So there's kind of the no outsourcing, no money coming from outside, no money going outside. That's non-trivial. I'm not gonna go into the details of how it's possible to do, but it's possible. So this is what the Italians did a few years back. It's possible. And now let's get to our main question, sort of the properties that we particularly interested in today. Social optimality. If you want to make the mechanism socially optimal, again, just socially optimal, forgetting about everything else, just trying to maximize the benefit to the society. Is it hard, or how hard is that? Well, you have to solve an optimization problem. So if you have this, yes, truthful reporting, if mechanism is truthful, as we discussed, for a social optimal mechanism, the mechanism should be truthful. But then you would have to solve an optimization problem. And well, I don't want to say that we know how to solve all optimization problems in the world, but at least we have some ideas. Some of them are complicated. For some of them, we do have algorithms and so on. So that's well, just a computational problem, just quote unquote. And last but not least, incentive compatibility. How on earth are you going to enforce that the users don't lie? So few slides before the answer, it's actually possible, but just again, the recap of all the four properties. So individual rationality and budget balance, each by itself, it's easy. All together, no, two of them together, possible but not trivial. For the mechanism to be socially optimal, it should better be incentive compatible, because you need to know the users or their preferences before we can maximize the evaluations. And how to do that? Well, here is the answer. Okay, and the answer is given in kind of purely quantitative terms in these formulas. We will dissect this formula towards the end of this lecture. But one important thing to take home is that it's possible. It's already quite striking that it's possible to do the mechanism which is socially optimal, that is maximizes the social welfare, and which is truthful. And in order to do that, you have to make the users pay like this. And oh my God, what's that? It's something complicated formula, but let's look at it. So first of all, it has some function which is really independent of the user, like the entry fee. So every user pays something to get into the market. And it doesn't matter of the preferences that the user submits. Whatever the user is, well, they have to pay something. So that's just some constant. And then the more important thing is the second term here. This is what the user pays. So we look at the valuations of all the other users. I'll clear the drawing and restart. So in this term, so these are the valuations of all the other users. So we are summing over all users but I. So we don't look at the user I. We look at what all the other users get from the mechanism, from their allocation. Okay, so that's just the formula. I don't know if it makes much sense by itself, but we will not prove it. But with this notation, it's just a straightforward substitution. You can actually see that this mechanism is truthful in that no user has an incentive to misrepresent his or her preferences. Okay, so the payment in the Vcg mechanism, which is named after Victor Clark and Grooves, which showed or developed this mechanism in a series of papers some 40 years back. So the payment of every user consists of this kind of fixed part, the entry fee, minus the total happiness of all the other users. And surprise, surprise, it makes the mechanism truthful. Okay, so we know how to make the mechanism socially optimal. Well, we just have to maximize, solve a computational problem. We know what prices we should set in order to make the mechanism incentive compatible. We know we cannot have all four properties, but we may try to make the mechanism individually rational. And in fact, it is possible. And for that, we can use the flexibility in this entry fee. So this is an arbitrary function, which is independent of the user. And by choosing this function in a smart way, we can make the mechanism individually rational. And in fact, we will see a rule which makes it individually rational and makes all the mechanism sensible. It will make sense how it is done. But before we look at that rule, let's look at some other choices for this function. One thing we may say, well, maybe the users don't pay at all for entering the market. So let's not charge them. So in this case, every user will pay this, well, minus the total happiness of everybody. And remember, minus payments means that the mechanism pays to the user. So the user pays a negative price. It is kind of a individually rational because, well, you want everybody to be very happy because then you get paid by a lot from the mechanism. So yes, it's individually rational, but that's probably too good to expect in practice. It's kind of too individually rational, right? Remember, we don't have to make the mechanism budget balanced. So we can say, oh, we have such a wonderful market. We will pay to everybody the total happiness of everybody else. Interestingly, then you will still not want to misrepresent your utilities or your valuation function, your preferences, and that makes the mechanism individually rational, but that's probably too unrealistic. What is more realistic and what does make sense is something called the Clarke pivot rule. So, well, in the Clarke pivot rule, you have the mechanism which is truthful mechanism. It's a Vcg mechanism, so it optimizes the social welfare. It has this form of the payment, but the particular choice of this entry fee of this function for user I is this, and let's see what it is. So this is the maximum possible happiness of all the users except I. Okay, so what does it mean? So what it means is that assume that user I is not in the picture. Okay, so we remove user I. What could be the maximum social welfare of everybody else? Well, that's what it is. You're maximizing the total happiness of everybody except user I. Okay, so let's ignore user I. Let's forget about him or her. Just maximize the happiness of everybody else. So that's HI. And here it is. And now the price that the user pay is this maximum total happiness without user I, so exactly this thing, minus the total happiness of everybody when the user I was in the picture, right? So here, the social choice function F chooses an allocation when user I is in the picture, so altogether for all n users. But we are summing up the happiness of all the users except I. And here we are optimizing when I was not in the picture. So these two things are almost the same, except that here we are removing the user I from the picture and then maximizing the social welfare. And here the user I is in the picture. So we are optimizing together with the user I, but then we are summing up the evaluations of everybody else except user I. I'll remove the drawings. Again, this is how much the society could have been happy if user I were not in the picture at all. And here is how much the society is happy when user I is in the picture. So in a sense, the price that the user I pays is kind of the harm that user I brings to the society. See, because of the user I, the total happiness of the society went down from this to this. So here we were maximizing, ignoring user I. That's how happy the society could have been. Here we're maximizing, taking user I into account, but only looking at the total happiness of everybody else, not the user I. And what user price, what the price that user I pays is the difference between the two, harm to the society. So now, all of a sudden, this makes a lot of sense. It's kind of fair. It's super surprise. Well, there are so many surprises. One surprise is that truthful mechanism exists altogether. Maybe second surprise is that, well, simple things like money make people truthful. We don't have to enforce anything else, don't have to go into people's heads, and so on and so forth. And the next surprising, I think, beautiful thing is this Clarke pivot rule, which sets the price to the harm that the user brings to the society. Quite fair. And the mechanism stays incentive compatible and, of course, socially optimal. So one other good property of Clarke pivot rule is that if you know how to solve this problem, how to, well, maximize the total user's happiness, if you can compute the social optimum, then you can also compute the prices. So computing the prices is not much harder. Here you're optimizing without user I, here you're optimizing with user I. But if you know how to solve this optimization problem, then you also know how to set the prices. Okay, so our running example, let's see how this Clarke pivot rule works in this case with the slot allocation. So again, just to remind you, or if you watch the video from this point, we have n users and slots, and the users are ordered with respect to their impatience. So this WI is how much user I loses when the slot increases by 1, from 1 to 2, from 2 to 3, or from S to S plus 1. And it's quite natural that we want to match the users to the slots in the order of their decreasing impatience. So now user I will get slot I. So the valuation of the user I over this resource allocation. So the users are completely selfish, rational, and envy-free. They only look at their own slot. They don't care about the slots of other users. So the valuation of user I, since user I gets slot I, this is what it is. It's CI minus WI times I. This is how much the user has to wait. And well, the total social welfare, or the total valuation of all the users, is just this. So again, this is just formulas. It's easier to write them than to pronounce. Okay, so that's the total social welfare of all the users. So let's see how much the user pays. So if user I is not in the picture, then, well, the users 1, 2, 3, and so on, up to I minus 1, will still get the same slots, right? User 1 will get slot 1, user 2, slot 2, and so on. User I minus 1 will get slot I minus 1. But user I plus 1 will get slot number I, because remember, user I is not in the picture, right? So everybody after user I will shift one slot up, right? So for the user number 1, it doesn't matter whether the user I is in the picture or not. The user number 1 will get the slot 1 anyway. User number 2 will get the slot 2 anyway, and so on up to user I minus 1. And only starting from the users I plus 1 and up to n, they will get different slots. They will get slot I and so on, n minus 1. So if you want to look at the maximum social welfare of all the users when user I is not in the picture, then the users before user I will get the same slot. Every user J will get slot J. So here is the formula. And all the users after I will get one slot less. So they will move up. Okay, so that's the total social welfare of the society when user I is not in the picture. Maximum, not just the total, but the maximum social welfare of all the users. And when user I is in the picture, again, remember we have to do the summation for the valuations of all the users. Well, in this case, again, the users up to I will get the same slots here and here. So this one will cancel when we subtract the blue from the red. And here again, we are summing for all the users except user I and users which are after I. Again, each of them, user J will get slot J. And when we subtract blue from red, then okay, all these CJs, they go away, and every WJ will be counted once, because here is WJ times J, here is WJ times J minus 1. So when we subtract one from the other, I'll clear the drawings. So when we subtract this from this, and remember each of these comes with a minus, well, you'll see that what remains is the sum of WJs for all the users after I. So this is the price that user I has to pay. Okay, a lot of math. I don't know if you followed right now, but you may follow yourselves more or less. Users before I get the same slots. User after I, everybody gets one slot up. So that's how much they lose. And here is the picture. Again, the users before I get the same slots, no matter whether the user I is in the picture or not. All these guys get the same slot. Oh, sorry, that was too far, not this one. But when user I is in the picture, then he gets slot I. When user I is not in the picture, then user I plus 1 gets slot I. And user I plus 2 gets slot I plus 1, and so on. So again, speaking in terms of the harm that user I brings to the society, what happens is that when you insert user I and user I gets slot I, everybody after user I gets shifted by one slot down, right? So user I plus 1 gets slot I plus 1, even though it used to have slot I, and so on. So everybody gets shifted. Everybody after user I gets shifted by one slot down. Hence, everybody loses their WJ, and the sum of the losses to the society is what the user has to pay. Okay, so we looked at this thing from different perspectives, the general formula, but also the specific thing with the slot allocation. That's kind of the end of the main part of the lecture, just some conclusion. So this is what I was talking about today. The different mechanisms, their different properties: social optimality, incentive compatibility, individual rationality, budget balanced. We know that you cannot have all four, and there has been work which does mechanisms with all but incentive compatibility, and we used Victor-Clarke groove Vcg mechanism to get the mechanism which is all but budget balanced. Interestingly, so Vickrey actually did get the Nobel Prize for it, but he didn't make it. He passed away a few weeks before getting the before he was supposed to get the Nobel Prize. And yeah, I mean, Tobias and I have been trying to get the Swedish recording of what was said about him. I was saying about all his contributions, in particular to air traffic concessions. I'm not sure what concessions means, or at least in this context, maybe it's air traffic congestion. Maybe. So it's also the auctions are used, of course, for spectrum and for many other things. And so they were all mentioned, but this air traffic concession is still a bit of a mystery to me. What was meant there? Maybe it's air traffic congestion. But anyway, air traffic was mentioned there. So I think I will not speak about, there is some difference in how the auctions are done in the US versus EU. I guess they're too technical to speak about. Rather, I will just finish, so we do have time, by mentioning some open problems and challenges. So of course, I was talking about theory mostly today, but when we get to the real life, yes, there are challenges of how to find the allocations and prices, with what algorithms, how do we compute them. What we were talking about today was assuming complete determinism, but we know that ATM and in general the world is well, stochastic and dynamic. That's not taken into account by the Vcg mechanism. There could be also other objectives and other properties besides the ones that we looked at. One thing which is, well, it was theoretically studied for quite a lot of time, and maybe it will make its way into also into practice as this kind of minimum regret optimization. So we are looking at the total social welfare, but we don't say how the welfare is distributed between people in the society. So the total welfare could be maximized by giving somebody a lot and giving very little to somebody else. So maybe we may want to have more equitable mechanisms. So that there has been some research on that. Next question is privacy. Yes, of course. I mean, this valuation is private info. No airline is willing to tell you what is their weight coefficient or impatience or whatever you want to call them. Many other things. So it's cool that there exist mechanisms that kind of solicit the truthful info, but it still doesn't mean users, as we know, and there is actually work on quantifying how irrational, how selfish and envious the users are and different agents, and they will not submit the true information even though they will lose. So there are these experiments, a lot of experiments, again, in, I don't know, game theory, economics, social science, whatever you call it. I'm not the expert in that, but I've seen some nice reports, and I think there are even papers. They would do an experiment like this. They would come to two people in different places, in different countries, so people don't even know each other, and they would say to one of them, well, here is $100, and it will be split between you and the second person whom you don't know, and you don't know who that person is. And the first person just decides the split, like 70-30 or 90-10 or whatever, 50-50. And then they come to the second person and tell him or her, there is this other person who made the split, who decided 70-30 or 50-50 or something. And you can accept this split, and then you get the smaller part and the first person get the larger part, or you can just say no, and then none of you gets anything. And you may assume that if somebody comes to you and tells you, well, I can give you $1, and there is this other person who will give 99 because they decided so, then you will say, okay, thank you for $1, and say yes. But surprisingly, people say no. And there is this quantification. I think they do it by countries, by income, by whatever. Uh, when is the threshold? So when do the people say no to kind of free money just because somewhere else there is this unfair person number one who decided to do the split in such an unfavorable way, getting 90 to himself and giving me only 10? Oh no, no way! I'm not going to accept that. So anyway, there are lots and lots of studies when they quantify different things like risk aversion, how people don't want to take risks, and so on and so forth. So all these questions are yet have to be answered. Yes, and then last but not least, the owner's profit. So we were talking about this owner, which kind of acts as a mediator and well, it's super fair. It's not trying to maximize their profit. That's not true. Very often owners want to maximize their profit. And then there is huge issues with monopolies. And there are all these papers and research on bargaining with the ruler and dictators and so on and so forth. Well, more questions than answers. Other settings, so we were talking about the airport slots. Of course, there are also slots. Well, you know, here I have this airspace, and a lot of aircraft want to cross it from left to right, and they have to go in bulks. How do you assign slots? Who goes first? Who goes next? And so on. And then of course, the implementation. Okay, so how do the users pay? Do they just, get the money from the sky? Who gets the money? LFV or Svedavio, whoever wants to run this auction, and so on and so forth. Right. So understanding that the preferences should be monetized, trying to get these delay costs, at least the reference values for the airlines, or have the airlines determine the cost themselves, looking at different objective functions. There is a whole a video which I'm not going to show in Zoom, but you may watch that about UDPP, user-driven prioritization process, which is something in Eurocontrol and Cesar, which is trying to address this question of mechanisms. It's called user-driven prioritization process because it's trying to say, well, instead of first come first serve basis, let the users submit the evaluations, get the mechanism decide who goes first and who is prioritized, but it should be user driven in the sense of users submitting bids. Last but not least, who is the user? I mean, we looked here at a per flight view. So flight was the agent, flight wants a slot, but of course there is a business entity which is an airline, and it has several users or several agents, several flights, and they may want to exchange the slots inside the airline, or more generally exchange the slots between the airlines. There are all these processes, all these questions, how this is done, and so on and so forth. And thinking of an airline as of a user is kind of going one step up, but in principle, the kind of real users are the customers, the passengers. And there are projects like this passenger-oriented evaluation metrics where they're really trying to go down to, well, the passenger level and try to see how much the passengers should be charged. Then, of course, there are questions as whether the passengers have any say, and is it reasonable to expect that, you will hear from your pilot, well, we are about to land and we can either be in a holding for 45 minutes, or if we gather up 5,000 euros from the whole aircraft, then we will be given a more favorable slot. You probably don't want to go into something like this, or at least it's unrealistic, but it's very realistic to expect that, there is a executive in the backseat of a business jet, and they are willing to pay to get a favorable slot. Well, why not charging them and have the players to be more active and make decisions. Anyway, lots and lots of questions yet to be answered, but at this moment, we'll probably stop and ask you if you have